Hello, advanced algebra students, and welcome back to another video lesson. Actually, make that the last video lesson of the year. This is it, last one for today, last new content, not really even new. Today, we're just going to continue to explore how do we solve using logarithmic function. So it's just expanding a little bit more from what we did yesterday as an introduction. All right, so let's recap what we've did in that previous video with this little bit of a warm-up. The population of the U.S. reached 300 million in 2006. Suppose that it grows at an annual rate of 0.86%. 0.86%. Write an equation in y equals abx form. What should our a value be? The a value, we can say it's going to be 300. We know that that's going to represent million times b to the power of x. B is this rate. Now be careful. 0.86% really is the decimal 0.0086. And that's what we're going to put in right here, 0.0086 to the power of x. So be careful with that percentage. Question B, when will the population reach 400 million? We want to know when will this equal 400, which represents 400 million. Because I used 300 there, I'm going to use 400 there. To solve this, we need to isolate the part that has the variable exponents. So we divide by 300. And we get 0.0086 to the power of x equals 4/3. Move the x out front from our properties. X times 0.0086. I can't even do that yet. I forgot a step. Let me erase that. We got to do the log of both sides first. We need the log of both sides first, Mr. G. We got to take the log of both sides first. That's going to give us x times the log of 0.0086 equals the log of 4/3. We can get x by itself by dividing both sides by that log of 0.0086. And that's the part we want to use in Desmos. So start by inserting your fraction. Log of 4/3 over log of 0.0086. I better put that into parentheses. And you'll notice that we get negative 0.06. Negative 0.06. So something doesn't quite seem right here, does it? All right, after careful investigation, I don't have the right b value. It's got to be 1 plus our rate. Remember that b value is 1 plus the rate for a growth. So I need 1.086. So we should really divide it by the log of 1.086. So I'm going to go back over here, and instead of 0.0086, add a 1. And there we go, 33.6. X equals 33.6. That means 33.6 years from the year we started with 300. So if we started with 300 million in 2006, the population won't reach that until 34 years later, or the year 2040. Until that year 2040. All right, now the main part from this is trying to remember that we're using log whenever we have x as the exponent. So here's a couple of extension problems from yesterday, similar to what we did, but some additional steps. Whenever you see the exponent value, we have to isolate that part before we can take the log of both sides. So we technically have to make sure that we add 5 to both sides first, or e to the power of x equals 17. Whenever we have e, we're going to take the natural log of both sides, and then it's x times the natural log of e equals the natural log of 17. The natural log of e, this natural log of e really becomes 1. And x equals the natural log of 17. Why does that become 1? Well, look over here really quickly. Log base e of e. E means whatever exponent this is what it equals. Natural log and e are inverses of each other. They basically cancel each other out like division does. So all we're solving is x equals the natural log of 17. So type in ln for natural log, type in 17, and we get 2.833. X equals 2.833. Okay, second one. Here is my exponent. N plus 10 is the whole exponent. So I got to isolate this chunk by subtracting 3. 9 to the power of n plus 10 equals 78. We're going to take the log of both sides, meaning the whole exponent comes out front. N plus 10, that whole exponent, times the log of 9 equals the log of 78. If we want to isolate this, how do we undo multiplying by log of 9? We divide both sides by log of 9. And we're left with n plus 10 equals all of that. How do we undo plus 10? We would have to subtract the 10. Or n equals the log of 78 divided by the log of 9 minus 10. And we can type that whole process into Desmos. Start out with your fraction. Log of 78 divided by log of 9, take away 10. Log of 78 over log of 9, take away 10, gives us negative 8.017. Negative 8.017 is our n. So anytime we have those variable exponents, we're trying to isolate the parts that has the exponent by moving, using addition or subtraction. Then we can take the log of each side so we can move it out front. Now, we also have something that's called the change of base theorem. The change of base. And what this does is it helps us to simplify how we go about solving these or evaluating them to the nearest 10,000th. And I've showed you this a couple of times in live sessions and videos. But basically, we have to do this because most of our calculators don't have this log base button of something else. Or if it does, most of the time it's disabled and locked, and we can't even really get to it. So what we've done in the past and what we talked a lot about is to rewrite this, we have 4 to the power of x equals 24. That's the exponential way of rewriting that. And what we just talked about now was, well, in order to solve, we take the log of both sides. Log of 4 to the x equals log of 24. Move the x out front. X times the log of 4 equals the log of 24, which means x equals the log of 24 over the log of 4. Notice this right here is very similar to this right there. If we have a problem where they're just asking us to evaluate the log of some base to another number, we can take what we call the change of base theorem and say the log of that whole number over the log of the base, which is what we showed in these steps here. So the log of 24 divided by the log of 4. The log of 24 over the log of 4 to the nearest thousandth, so 3 decimals, 2.292. 2.292. Why don't you see if you can do letter B? All right, we're trying to figure out what that equals. Because I don't have anything else, we can just use the change of base theorem, log of 130 over the log of 5. We're going to have to use decimals to help us with that. Log of 130 over the log of 5, 3.024. So we can use that change of base theorem when we're just trying to evaluate a log problem. All right, hopefully that makes a little bit more sense. Occasionally, though, we might not have to use them when we have E. Right? Anytime we have E, we really should be using natural log of both sides. So the natural log of E to the power of X equals the natural log of 24. The X comes out front. X times the natural log of E. But this part becomes a 1. So X equals the natural log of 24. If we figure out that natural log of 24, 3.178. 3.178. And again, this is set up differently than those other ones with the change of base. Now, letter D, we have to be a little bit careful. What do we need to do first? We do have to isolate that e to the power of x by dividing by 5. E to the power of x equals 33/5. And now we can take the natural log of both sides and say x times the natural log of e. But we know the natural log of e should be changing to a 1, or x equals the natural log of 33/5. Let's go figure out what the natural log of 33/5 is going to be. 1.887. 1.887. And hopefully you can see the process in a lot of these is very, very similar. It's being repeated over and over and over again. All right, here's our last example for the year. Last one, we're going to finish with money. If your money is compounded continuously over and over and over again, what interest rate, what R value, is needed for your money to triple in 20 years? Your money to triple in 20 years. And so we're still using this formula. A, the total amount at the end, has to equal our principal times the E. E we're using because that's that constant continuous compound to the power of RT. And then we're going to fill it in. And the filling in part is a little bit tricky. When we fill this in and we're trying to triple our money, we're going to imagine we started with $1. That's our principal, $1. And if it's going to triple, we want it to go to $3. E to the R, because I don't know my rate, it's asking me to find the rate, to the power of T, 20 years. And now we got to work on solving this for R. Right? 1 times all of that. I got to isolate this part. So we would divide by 1 and 3 equals e to the power of r times 20. If I have e to some power, we take the natural log of both sides, or the natural log of 3 equals r times 20 times the natural log of e. Natural log of e, as we've just been describing, is 1. So the natural log of 3 equals r times 20. How do I get r by itself? We divide by 20. So the rate will equal the natural log of 3 all divided by 20. The natural log of 3 all divided by 20. So I'm going to start by inserting a fraction. And on the top, it's the natural log of 3 being divided by 20. And we get 0.0549. 0.0549. What percent is that? What rate? 5.49%. Converting it back to that percentage. If you do have any questions about solving using logarithms or the change of base theorem, please make sure that you reach out and ask. Otherwise, until next time, everyone, stay safe.